This is our first session in a new unit about electrochemistry. You can check this out in your book, section 17.1, but this video is also going to be about balancing redox reactions. And so you can also go back in your book to section 4.2 and reread about redox reactions if this is a little rusty for you. So what is electrochemistry? So from the words electrochemistry, this is the interconversion of chemical energy and electrical energy. And if we think about chemistry and we're moving electrons around, that is redox chemistry, oxidation and reduction. So where might you find electrochemistry? Pretty much everywhere. Batteries are electrochemical cells. The idea of corrosion or oxidation, so like why is the Statue of Liberty green? Why do things rust? How do we keep things from rusting? All sorts of biological processes, especially the ones that give you energy, like respiration, like photosynthesis, are redox processes, are electrochemistry. If you or somebody you know uses a blood glucose meter, those use redox chemistry. The pH electrodes used in labs, those use redox chemistry. So redox chemistry is everywhere, electrochemistry. And our goal over the next several sessions is to figure out a little bit about how that works. So in order to understand redox chemistry better, we need to get used to recognizing it in reactions. So here in this reaction, in which oxygen reacts with iron to form rust, we can assign oxidation numbers. So if we start here with the oxidation number of iron, we'll do this for each element. The oxidation number of iron here is 0 because the oxidation number of an element in its elemental form is 0. The oxidation number of oxygen in O2 is also 0 because oxygen is an element, that's its elemental form. And then we get to iron oxide, and now we have to treat the oxygen and the iron differently. So, in a compound, oxygen usually has an oxidation number of -2. And then we can figure out the iron by difference. So since there are 3 oxygens, that's a total of -6. And we know that this is overall neutral, so the iron has to balance that -6. Since there are 2 irons that have to equal -6, we know that or equal +6 in that case, because it has to balance the -6. We know that the oxidation number of iron has to be +3. Okay. And so we can assign oxidation numbers for all the atoms, and then look at which atom's oxidation number increases. So the iron atom increases because it goes from 0 to +3, and the oxygen decreases because it goes from 0 to -2. So here are the rules for assigning oxidation numbers so you can keep doing practice. Remember, atoms in their elemental form, oxidation number of 0. An atom in a monoatomic ion has an oxidation number identical to its charge. So, for example, in chloride, chlorine has a -1 oxidation number. An atom in a polyatomic ion or molecular compound usually has the same oxidation number it would have if it were a monoatomic ion. So, for example, hydrogen in a compound usually has a charge of +1, and then the sulfur here would have a charge of -2 in order to balance that out. Oxygen usually has an oxidation number of -2. It can also be 0 or -1. And halogens, so like chloride, usually have an oxidation number of -1, but they can be different. There are more exceptions to that. And remember that all of those oxidation numbers have to add up to 0 for a neutral compound, or whatever the net charge is. Okay, so oxidation and reduction reactions they always happen in pairs. They have to go together. If one thing is oxidized, the other thing must be reduced. And so remember what oxidation and reduction mean is that oxidation means something is losing electrons, so its oxidation number is becoming more positive, and reduction means gaining electrons, or its oxidation number is becoming more negative. You can remember that using a couple of acronyms. I went to college in Oklahoma in oil country, so I remember oil rig. Oxidation is loss, reduction is gain. Maybe high school you remember something about a lion. Leo the lion goes grr. Losing electrons is oxidation. Gaining electrons is reduction. Okay, we can also identify the reducing agent and oxidizing agent. So the reducing agent causes reduction of the other thing, which means that it itself undergoes oxidation. An oxidizing agent causes oxidation of the other thing, meaning the oxidizing agent itself undergoes reduction. So let's see how it plays out in an example. In our example before, we identified that the iron was increasing its oxidation number, which means it is being oxidized. Oxygen is decreasing its oxidation number, which means it is being reduced. So since iron is being oxidized, it is the reducing agent. Since oxygen is being reduced, it is the oxidizing agent. Okay, so test yourself. Can you identify the reducing agent in this reaction? Okay, so if we look at oxidation numbers, these are pretty easy to identify because we have these ions with charges. So the irons are +2 and +3 because those are the same as their charges. This chlorine is 0 because that's its element form. And this chlorine is -1 because it's chloride. It's the same as its ion. Okay, so we see that iron is being oxidized and chlorine is being reduced. So the reducing agent is the thing that is causing reduction of chlorine. So the reducing agent must be iron 2+. And it's iron 2+, not iron 3+, because the reducing agent or oxidizing agent is always the reactant. Okay, so our next goal is to balance reactions for redox, balancing redox reactions. And the way that we're going to do that is we have to balance not just the atoms, but also we need to think about the electrons. So we're going to separate the reaction into two half reactions, balance those, and then combine them again, where one half reaction describes oxidation and the other half reaction describes reduction. So let's do an example. So here we have dichromate plus iron 2 goes to chromium 3 and iron 3. So our first step is we're going to divide this into two half reactions. And how do we decide what to put together? Well, so we see that we're going to put the two iron things together. So we have iron 2+ goes to iron 3+. And we have dichromate goes to chromium 3+. So we put the chromium atoms together and we put the iron atoms together. Now, next step is to balance all of the atoms that are not hydrogen and oxygen. Okay, so if we start here with the chromium one, we see that we have two chromiums in dichromate, so that means that we need a 2 in front of the chromium 3+. If we go over to now all of the atoms except for oxygen and hydrogen are balanced. If we go over to the iron 1, we see that we have one iron 2+ and one iron 3+, so those are good to go. Okay, so next we're going to balance the hydrogen and oxygen atoms. All right, so here if we add so we have oxygens, so we need to balance the oxygens by adding water molecules to the other side. We'll add 7, so that way there's 7 oxygens on each side. Okay, but that creates a problem because now we need to have more hydrogen atoms. So we'll add 14 hydrogen atoms to the reactant side. Okay, so now all of our atoms are balanced. We need to balance our charges. Let's do that. We've got on the reactant side, if we add up all of the charges, we've got 14 pluses and 2 minuses. So that's a total of 12 plus. On our product side, we've got 2 3 pluses, so that's a total of 6 pluses. We need to make those match, but we can only add electrons to balance them. We can only add negatives. So we take the more positive side and we add enough negatives, in this case 6 electrons, so that the charges are equal. The charges don't have to be 0, they have to be equal. Okay, so if we put all that together, and I'll rewrite a little bit so it's easier for us to see, we've got 14 H pluses plus dichromate plus 6 electrons goes to 2 chromium 3 plus 7 water. Okay, and that 6 electrons makes sense because we've got our oxidation number of chromium on the reactant side is +6, and our oxidation number of chromium on the product side is +3. We've got 2 of them. So we're changing each one by 3 electrons. So chromium is gaining 6 electrons in order to form chromium 3 plus. Okay, so that half reaction is done. Let's go do the iron half reaction. We mentioned before that the atoms here are balanced. So the iron atoms are balanced. The hydrogen and oxygen atoms are balanced because there aren't any. Now it's time to balance the charges. We have a +2 charge on the reactant side and a +3 charge on the product side. We go to the more positive side and add electrons until we can make it match. So we're going to need to add 1 electron. Alrighty, so now those charges are balanced. It's time now to recombine our half reactions. We're going to add these together, the chromium one and the iron one. But before we're ready to do that, we need to make it so that the electrons are going to match on both sides. So that, since we have 6 electrons in one reaction and 1 electron in the other reaction, we're going to have to multiply this reaction by 6. Okay, so now we're ready to recombine our reactions. So we're going to have 6 iron 2 pluses plus 14 H pluses plus dichromate plus 6 electrons goes to 6 iron 3 pluses plus 2 chromium 3 pluses plus 7 waters. Oh, at plus 6 electrons. Almost forgot those. Okay, so our 6 electrons cancel as they should. If your electrons don't cancel out, something is wrong. And then we can rewrite that one more time to make it extra pretty. 6 iron 2 pluses plus, and I'm going to put the chromium in front just because the H pluses are sort of less important. But remember, it doesn't really matter. Goes to 6 iron 3 plus 2 chromium 3 plus. Alrighty, and so if we look at this balanced reaction, we'll see that we've got 6 iron atoms on each side. We've got 2 chromiums on each side. We've got 7 oxygens on each side. We've got 14 hydrogens on each side. Our charge on the left side, total charge, is 12 plus 14H plus minus 2 is 24 pluses. And then on the product side is, let's see, that's 18 plus 6 is 24 pluses. This reaction is balanced. Okay, so you can see all of the instructions for doing all of that. And so I want you to do some extra practice. You can also look for some extra videos where we deal with some special cases related to balancing redox reactions.